Adams was already online, so I don't want to take. If we can start early, I guess that's good. But he's going to be talking about something that's very interesting, which is all of the observation of comets that have come serendipitously from watching from other missions that NASA has going observing the sun. And are you ready to go, sir, or do you want to stand by?
I am good to go.
Okay, well, let me turn it over to you, and I bet you can push the buttons better on your side than I did. But we're very happy to have you with us. Thank you very much for taking the time to talk to us.
Yeah, I appreciate it. Let me bring up my... okay, well, I appreciate you guys inviting me to talk to you all again. I've actually spoken to your club a couple of times over the past, I guess, 10 or so years. Usually on kind of this sort of theme of stuff. But what I figured I'd talk about tonight is what I'm calling the serendipitous science. This is science that has come out of sun watching spacecraft that are designed purely for watching the sun and nothing else, but have inadvertently yielded an absolute wealth of science, primarily about comets. But as you'll see, I drift a little bit from comets as well, into dust and asteroids, but it's all kind of around this theme of unexpected science. But what I wanted to begin with, because I thought this was kind of an interesting history. I've never seen someone put this info down on a single slide before. Comets from space. I did a little bit of searching, and it turns out the first comet ever observed from space in any way at all was comet Tago-Sato-Kosaka. Probably butchered that name, but it's a comet I've never heard of. But it was seen basically as a fuzzy hydrogen cloud in ultraviolet images from the OAO observatory back in January 1970. So this is the first time that anything in space, any kind of spacecraft, had captured essentially a detection of a comet. Fast forward like 3 years, and there's the Skylab kind of space station that was up there for a while. They actually recorded the first ever direct images of a comet, and that was Comet Kohoutek, which probably a lot of people listening are familiar with. At least that was a comet that promised a lot and didn't deliver quite as much as hoped. But that was seen by coronagraph telescopes on Skylab in 1973, and then the very first comet actually discovered from space was a comet that was originally labeled Howard Kuhlman Michaels Sheely. George Doshek will be familiar with all of those names for sure. I've worked with 3 of those guys. They worked at the Naval Research Lab with me. It was an NRL coronagraph on the Solwind satellite in 1979. So this bright streak over here is the comet. So really in this one decade, you go from 1970 to 1979, and you go from the very first detection of a comet from space all the way to actually discovering a comet from space. And that kind of started to set the scene of discoveries from space. So this Solwind mission that I talk about, it ran from 79 to 84. The telescope that was of interest for comets was this, what's called the white light coronagraph, this thing here. And actually the comet discovery that it made was actually the first space-based discovery of any solar system body. Like nothing had ever been, no planets, asteroids, comets, nothing had been discovered from space until this one in 79. And Solwind actually went on to discover a handful of these so-called sun-grazing comets that blazed past the sun. There was some overlap with another mission then, 1980 to 89, called SMM. I think it was Solar Maximum mission. This was another coronagraph that's looking in white light, so essentially visible light. And again, several more sun-grazing comets were observed. And it's kind of at this point that scientists start to realize that hey, we're going to be watching the sun we're probably going to see a few comets turn up. Like, we don't really care about comets, but it's kind of cool. We're going to see comets turn up from time to time. So they were kind of excited about that. But things really, really changed big time in 1995. And that was, this is a mission that I've talked about at length. So if you've seen any of my other presentations, you'll know all about SOHO. But the Solar and Heliospheric Observatory launched December 1995. It's at the L1 point in space, so it's just kind of between Earth and the Sun, pretty close to Earth. SOHO has more than a dozen instruments, again, designed exclusively to study the Sun, the solar surface, magnetic fields, and such. It's still operating today, so we're in the 30th year of operations, just in a very limited mode. And in terms of solar physics as well, but particularly here in terms of comet science, SOHO absolutely changed everything. It completely changed everything. And most of those changes were thanks to the telescope that's on SOHO called LASCO. This is the chronograph that my group at NRL developed, and we run it. It was actually designed and built in the late 80s, early 90s, and still routinely observing today. It's really one of only two instruments on SOHO that still routinely observes. And the instruments that we're going to be focusing on with LASCO is these two chronograph telescopes, LASCO C2 and LASCO C3. They're both use this solid disk in the center of the image to block out blinding sun. So it's basically just a false eclipse, so that you're not blinded by sunlight. You can see all the faint stuff that's coming out of the sun. You see coronal mass ejections and outflows, and you can see stars in the background of the C3 image. And just by luck, also, because they are so very sensitive to faint stuff that's near the sun, any small comet or big comet that goes near the sun that otherwise would be invisible from Earth, because we can't look at the sun during the daytime, we see them in these cameras. Now, a little side note, because this will become kind of relevant later when I talk about another mission. One of the reasons LASCO has been operating for so long is not actually so much because of the science that it's returning, but believe it or not, it was actually identified as of critical importance in national security. So in 2020, the ProSwift Act of Congress was signed, and ProSwift was kind of centered on what we call space weather. So the potentially hazardous effects of like solar flares and coronal mass ejections and things. And SOHO is the only telescope that we have between the sun and the Earth that's looking at these ejections and seeing these eruptions that might be coming towards Earth. And so there was kind of some fighting about is it time to retire LASCO? And the space weather community, the people that monitor the sun for harmful activity, they kind of argued that we need, until there's a replacement for LASCO, we cannot let LASCO disappear. So this will become relevant later on in the talk, but I just wanted to kind of point that out now, that it's even though it's full of science, it's actually technically a national security telescope at this point. But the cool thing about LASCO, as I was saying, because it's so very sensitive, we get to see all these faint things near the sun, and consequently, SOHO is history's greatest comet discoverer by far. You see in this animation, there were some comets going in, another bright comet flying in there. As of January of this year, SOHO has discovered 5,147 new comets. And just to put that in context, that's more than 2/3 of all documented comets that we have on the books. Like, I think in total there's maybe 7,500, maybe 8,000 comets that we've officially documented, and over 5,000 of them belong to SOHO. It's extraordinarily effective at seeing these teeny tiny little comets that are going into the sun. And this is all accomplished with citizen science. So I run this program called the Sungrazer Project that allows citizen scientists to look at the SOHO images and report comets and get credit for discovering comets. So the majority of these 5,000 comets have actually come from citizen scientists. So this is another presentation that I've given many times in other contexts. I'm not going to talk anymore today about the citizen science stuff, but you're certainly welcome to visit the website and reach out to me if you have questions about that. But what I wanted to focus on here today was not, like I say, not so much about these teeny tiny little new comets that SOHO discovers, but some of the really big comets that we've seen, and not just with SOHO as well. In just the first 10 years of operating SOHO LASCO, there'd been a bunch of big comets come through, like Yakutaki 96. We see 96P every time it comes around the sun, every 5 or so years. Kudo Fujikawa, Neat, Bradfield. I'm sure to many of you guys, these comets are very familiar to you. This was just the first 10 years, and since then we've seen a whole bunch more. But these kinds of observations really kind of clued everyone in that, like, hang on, this telescope is really seeing some really cool stuff. But until this point, SOHO was kind of alone in this regard. It was the only solar spacecraft operating that was seeing big comets. Then in 2006, the STEREO mission was launched. STEREO is a Solar Terrestrial Relations Observatory. It's actually 2 identical satellites that are sort of following around Earth's orbit at different rates. STEREO is actually down to 1 now. We lost one of the spacecrafts in 2014, but the other is still operational. And on STEREO, we have coronagraphs, very similar to what I was just showing you with LASCO. But we also have these kinds of cameras called heliospheric imagers. And this diagram sort of illustrates the field of view of these heliospheric imagers. Rather than a telescope that is centered on the sun, a heliospheric imager keeps the sun outside of the field of view. So the sun in a traditional coronagraph is over here. Then you will have like these big square fields of view that are off to one side. That are still looking close to the sun, but that you don't have to worry quite so much about stray sunlight getting in there. Consequence of that is we can get far deeper exposures. These cameras are even more sensitive than SOHO is. And this development of technology has led to absolutely remarkable comet imaging sequences. Just after launch, this sequence on the left here is Comet McNaught. Early 2007. This was literally a few days after we first started operating this telescope in space, and this comet goes blazing through our field of view, and that had all of our jaws banging onto our desk when that came through. It's I still think it's one of the most amazing comet image sequences ever recorded. I know the striated tail of McNaught was a very famous defining feature, and that's something we need to keep in mind, because a little bit later on in this talk I'll be returning to kind of the science of these striations. But also in STEREO, a few months after Comet McNaught, Comet 2P Encke, which it's a regular visitor, we see that all the time. But we saw something really amazing in 2007. We saw a coronal mass ejection sweep over the comet and rip the tail right off the comet. The tail obviously grew back. The comet is completely unharmed by this. But again, this was another observation that was completely unique. And what we learned at that point is that we can use cameras like this to look at how the solar winds, the outflow from the sun, coronal mass ejections and such, are driving the dynamics of comet tails, the morphology of comet tails. And it turns out that for scientists that study space weather and the sun, comets are essentially a windsock. Like, you can look at the tails and see how they're reacting and get an idea of what's going on in that environment. So this, again, opened up a whole new domain of study that we weren't even really anticipating. Now, continuing on this chronology, the next satellite that came along that also opened up a whole new unexpected domain was the Solar Dynamics Observatory in 2010. Now, this one, unlike Stereo and SOHO, this one actually is looking directly at the sun. It's an extreme ultraviolet solar disk imager. So it's looking at the solar atmosphere at temperatures of tens of thousands to several millions of degrees. So it's looking at the super, super hot solar atmosphere. This is not the kind of environment where you would expect to see a comet. So in early 2011, we were absolutely stunned when a bright sun-grazing comet that was discovered in the SOHO images was actually observed plunging into the solar atmosphere, and we actually got to watch it in extreme ultraviolet light, kind of fragmenting and completely vaporizing. And this was the first time in history that we've actually witnessed a comet vaporizing in the solar atmosphere. And that kind of got us thinking that, like, wow, like again, there's this whole new domain. It's actually possible to see comets in extreme ultraviolet images. We had no idea of this, and then it kind of left us wondering, well, how long are we going to have to wait before we get to see another one of these? Fortunately, the answer to that was just a few months, because December of that year, Comet Lovejoy, which is another sun-grazing comet, was observed in extreme ultraviolet light, actually plunging through the million-degree solar corona. So this is a solar atmosphere at like a million or so degrees. You see all the coronal loops and stuff, and this kind of cloudy thing, which hopefully is looking good on your screens. That is actually Comet Lovejoy plunging through, and what you're seeing here is all of the dust that is coming off of the comet. The dust is getting ripped apart into its constituent atoms very, very quickly. And the iron component of that dust is getting rapidly heated up to the million-degree coronal temperatures and is clinging to the magnetic field line. So you kind of see these little lines there where this iron is clinging to these field lines just for a few minutes and is locally enriching that part of the image. So we're actually getting to see like the signature of a comet going through. These are completely unique observations. There was a whole bunch of science that came from these. Like, again, solar physicists use them to study things like electron densities and temperatures, and there was just a wealth of science that came from this. Once again, we absolutely did not even anticipate that this might be a thing. So this was another one of these huge surprises from a mission that we didn't expect to return much for comet science. Now, the next mission, again on this chronology of impactful solar missions, is Parker Solar Probe. This is the NASA mission that is flying ridiculously close to the sun at ridiculously high speeds. It was launched in 2018. What you're seeing here is NRLs is our camera. It's called Whisper is the camera. It's a pair of these kind of heliospheric imager type cameras. The image of the sun there is the true apparent size of the image of the sun as seen by Parker Solar Probe as it's flying past the sun in one of its encounters. This one is from June 2023. But again, you can see that the Whisper camera is remarkably sensitive. Like, there's a very dense star field in the background. You see all this crazy solar outflow that's coming from the sun as we go past it. The Milky Way is in there at some point. All of these white streaks that you see flashing across the image, they're actually dust. Where the Parker Solar Probe has a big heat shield on it, and as it's flying past the sun, it's plowing into a lot of dust, and that dust is causing stuff to come up of the heat shield, and so the white streaks you're seeing are actually essentially pieces of a heat shield, which we're told is not harmful to the spacecraft. But then, and you see again all this amazing like solar structure as we're flying close to the sun. So Whisper is an extremely sensitive camera, and I'll be demonstrating that in a little bit with some science that came from it. Just pause that a moment. But WISPR has, because it's so sensitive, it has seen a number of comets. It's seen a bunch of small sun-grazing comets. It's discovered a bunch of small comets already, and it has seen several known comets. One of my favorite images is 2020 F3 Neowise. It was a really nice image we got of that. I know this isn't comet related, but I love this image too. When PSP uses Venus flybys to get into its orbit, and this is actually the night side of Venus, and we were actually able to see ground topology through Venus's clouds on the night side. So that was a whole other science paper, as you can imagine. And yeah, just in past December, PSP made its closest approach to the sun so far, 3.8 million miles from the solar surface, which is absurdly close, traveling at about 120 miles per second. So it's moving along pretty quick. Okay, the last space mission I want to talk about before I get into some more of the science is what I'm calling the LASCO killer. This is a telescope called SECOR-1. So if you recall how a few minutes ago I was talking about how LASCO is this kind of important for national security, we need to monitor solar eruptions kind of thing. For a long time, we've been working on launching a coronagraph to replace LASCO, and a coronagraph that is there purely for operational reasons. And when we say operational, what that means is it is not for science, or its goal is not science. Its goal is purely just to monitor and send back images. What people do with those images is up to them, but it's just simply to keep taking pictures of the sun and coronal mass ejections and stuff, so that the space weather forecasters can follow these things. So that is what SECOR does. It was, or SECOR-1. It was launched last year. These are some of the first few images from it in October last year. It's the first in a series of coronagraphs that are going to do this. There's one that's going to launch later this year that's going to be at L1 where SOHO is. There's one several years from now that's going to go to L5 on ESA's visual mission. As you can see from these images, SECOR is very sensitive. It's returning these beautiful views of the solar outflow, coronal mass ejections. It's already seen many sun-grazing comets. It also last year captured a spectacular sequence of 2023 A3, and you guys are actually going to get to be the first public group to see that sequence. We pub released the movie a short time ago, and you get to see it for the first time in a little bit. It's a really amazing sequence. So there's obviously a very obvious common theme to all of these missions that I've just talked about, and there's a couple of other missions I didn't get into just for reasons of time, but the point is, none of those missions that I listed, even all the way back to 1970, nothing there was intended for studying comets or discovering comets or looking at comets. It's 100% heliophysics missions with one focus and one focus only, which is the sun. So everything comet related that we've seen and learned from all of this is what I'm calling the serendipitous science. So what I'm going to do now in the second half of this talk is kind of dive a little bit more into some of the science that we've learned. This is obviously only a very cursory brush across the top of it, because pretty much every slide I show could be a presentation in itself. But I'll start with the comet tails, because they're always kind of cool to watch, and the solar wind and coronal mass ejection interaction. So I talked about Comet Encke getting his tail ripped off. This was the first direct imaging of a CME-driven comet tail disconnect. I mean, we've seen from the ground, there's been observations where you could see like plasma tails had disconnected and stuff, but no one had ever actually captured images where you can see the CME crossing over the comet. You see the tail disconnect. So as you can imagine, that created a flurry of analysis from solar physicists, and they basically determined that they think that the process there is something called magnetic reconnection. Essentially, the magnetic field, or the very tangled magnetic field that's embedded in a coronal mass ejection, passed over the comet and interacted with the magnetic field that was already draped around the comet, and through this process we call reconnection, essentially ripped off the plasma tail of the comet, which grew back. And this was the first time we really got to kind of study this stuff in detail, because we actually got direct images of it. And likewise, like this is, I have so many movies that are similar to this of comets in our images where the tails are just flapping away in the solar wind. This one happens to be F1 Lonius back in 2007. But we see so many that have these extreme interactions with the solar wind, where the tail is like furiously flapping away. And this process is still kind of under investigation. There's still a lot of modeling efforts that are ongoing to try and figure out sort of the specific physics of what's going on. I mean, a couple of popular theories for what's happening is that that maybe within the solar wind, which is kind of this constant outflow of material from the sun, there are essentially eddies of material. So you've already got these kind of turbulent patches within the solar wind, and as one of those hits a comet, it grabs some of the plasma, comet plasma, and takes it with it, and that's why you get these wiggles and these blobs. Another theory is that it's the process of the solar wind flowing over the comet is essentially inducing vortices, kind of like magnetic vortices behind the comet, almost like, so like if you imagine a rock in a fast flowing river, you'd get sort of a swirl of water behind the rock. Sort of that would be kind of the analogy here, that then these vortices are forming behind the comet, which are then picking up the blobs of plasma and then moving away from the comet. It's possible that both of these processes are ongoing. It's very likely that they are. It's a combination of factors. But the point is, none of this was really easy to study until you had an actual heliophysics satellite that was looking at these things, something that was designed to look at the solar wind, and then you can actually study these interactions. So also on the subject of comet tails, I showed you that stunning movie earlier of Comet McNaught from Stereo in 2007. This is a still frame from that sequence with a bunch of image processing applied to really enhance all of the striations that you see in the tail. And this tail was really one of the defining features of this comet. I mean, the internet is full of stunning ground-based pictures where the tail is arcing across the sky, and there are all these striations in there. Stereo happened to be very close to the comet, so it really got a very detailed look at the fine structure of this tail. And there'd always been sort of some debate about exactly what causes these striations, but the process that we think is going on is that the comet is shedding dust grains, and as these big chunks of dust come off of the comet, they fragment, and then these little fragments themselves would fragment, and that process continues. It's something we call cascading fragmentation, and essentially each of these events leaves a dust streak that ends up leaving a trail. And in a recent paper, it's actually shown with these images from Stereo, you can infer the rotation rate of the nucleus from the rate of these striations, which is a really cool result. What's also very unique about what Stereo showed with the striations is, I don't know if you guys can see it on your screens, but there are these kind of lines going radially out, like crossing the striations, almost like someone has taken a fine-tooth comb and dragged it across the tail. And that's sort of what I've zoomed in over here on the right. You sort of got this crisscross pattern. And what was interesting is that was not present in the comet tail until around January 14, 15 of 2007. And what happened around that date is the comet crossed what we call the heliospheric current sheet. It's sort of, I don't have time to really kind of get into what the heliospheric current sheet is, but essentially the comet crossed a magnetic polarity boundary within the solar system, going from essentially sort of north polarity to south polarity magnetic field, and the dust that was released after it crossed that boundary had these striations going through it in a separate direction. And so that was telling us that these dust grains are being affected by what we call Lorentz forces. So essentially you've got charged dust grains again dragged out by magnetic fields. And this is something that, again, is completely new. We didn't know this sort of process occurred. We could have theorized it, but a heliophysics mission this close to the comet actually provided the detailed images that there's no way you could get these from the ground, because the comet was very close to the sun at this time. So this is another example, again, of something that is just pure dumb luck on our part, to have these cameras that are designed to do one thing and we can get a different science out of it. So the next one, Comet ISON, I think most people are going to be fairly familiar with Comet ISON. This was the big disappointment at the end of 2013, when we were all hoping for something remarkable and spectacular that never seemed to be. So ISON was a sun-grazing comet that vaporized right by the sun. So after it goes past the sun, all that's left is this dusty cloud. Of course, we obtained some spectacular images from a whole bunch of different telescopes. These are just images from C3, C2, and from our stereo coronagraph as well. But what was cool, there were many cool things about these images, but one of the neat things about these cameras is they all have slightly different filters on them. And these filters all have slightly different responses to different wavelengths. So we can actually study the apparent brightness of a comet over time and compare it in these different filters. And that gives us kind of an idea of some of the processes that are going on. And in the case of Comet ISON, we're able to use that data to determine the exact time that Comet ISON basically completely destructed, exhausted its volatiles, and effectively became a dust trail. And the information, I'm not going to get too much into like complicated plots, but essentially on this plot, the vertical axis is brightness. So the higher up you go, the brighter it is. And then along the bottom, it's the distance from the sun. So 0 means the comet's closest point to the sun. So as you go left to right, is getting closer to the sun, then moving away from the sun again. What I want to point out is this orange curve. This is data from an orange filter that we have on LASCO. And that orange filter is very responsive to sodium emission. And we see that before the comet reached the sun, the sodium emission peaked and then started falling off quite rapidly. We also have, if you look at this blue curve, this is another SOHO filter. The blue filter is responsive really only to dust. It's really showing only the reflection of sunlight from dust. There's no emission or anything in the blue. And what's interesting about the blue is that still continued to increase while this orange, which was the emission, was decreasing. So essentially what this picture is telling us is that in this comet, suddenly emission of sodium or whatever started to dramatically fall. Meanwhile, dust was dramatically increasing. And the obvious picture that paints is that the comet has completely disrupted. It's just essentially crumbled into a huge dust cloud that is rapidly boiling off all of this volatile stuff, and it's essentially dying. And all you're left with is is a faint dusty debris trail streak in the images. That was, of course, very unfortunate for Comet ISON. And I have a whole separate presentation about ISON. I could talk for a couple of hours about that one. But again, we get this, it's still part of this picture of we have these instruments that are designed to do one thing, and with just a little bit of tweaking and reinterpretation, we can get this whole new set of science out of them. Now, in the case of Comet ISON, of course, the seeing that dust trail was bad news. That made us kind of sad when all was left with dust. But sometimes dust trails can be a good surprise. So these next few slides are kind of a theme of some new research, and this is related to Parker Solar Probe. So again, this is the NASA mission that's flying super close to the sun. We have our Whisper camera on Parker Solar Probe. Shortly after launch, when we were looking at the very first set of data that we got back from Parker Solar Probe, we saw that there was a really faint dust trail that crossed the field of view as the spacecraft was moving. You can barely even see it kind of between these dotted lines in these images. When you watch it in an actual movie and kind of squint a bit, you can see it kind of clearly. And we were puzzled because there wasn't supposed to be any like debris trails or anything in our field of view. So we did a little bit of digging, and we quickly showed that the dust was almost perfectly, and I say almost perfectly, following the orbit of asteroid 3200 Phaethon. And I say asteroid in quotes there because Phaethon was always assumed just to be an asteroid, and that's because from the ground it has always looked and acted like an asteroid. It does get extremely close to the sun, and for a couple of weeks of its orbit, no one can observe it from the ground because it's far too close to the sun, but you just assume, hey, it's an asteroid, it's just doing asteroid things when it's near the sun. But because of our stereo cameras and their super sensitivity, in 2009, we saw Phaethon when it was really close to the sun, and it turns out that for 3 or so days, it actually grows a small tail. This was a big surprise. In fact, it was a huge surprise. It was very exciting for the community. Again, a whole flurry of science papers came from it. And people assumed that, oh, so Phaethon must actually be one of these so-called active asteroids. It gets close to the sun, and for a few days, it actually kicks up some dust. And so that's why we get this dust tail from Phaethon. So you might think, well, that kind of explains why you would see a dust trail close to the orbit of this asteroid. Like, so Whisper is seeing the dust trail from this asteroid that produces dust. The problem is, in a couple of papers that we published recently, we're able to prove without doubt that the amount of dust in that trail is far more than Phaethon is producing, far more than it's capable of producing. And also that dust actually didn't perfectly follow its orbit. It's very, very close, but it didn't perfectly follow the orbit. So if this dust trail isn't directly from this asteroid / comet, what is it? Well, a little side note real quick about Phaethon. Some of you may know the story of it already, but for those that don't, it's an asteroid. Like I said, it gets very close to the sun. It's like every 3 or so years, something like that. It's a fairly short period. It's assumed to be the parent of the Geminid meteor shower. So the Geminids are the big one we see every December. That's the one that everyone gets excited about. They talk about it in the news and such. Basically, from the analysis of the orbit of Phaethon, and people have calculated the orbits of the individual Geminid meteors that we see in Earth's atmosphere. Folks have figured out that these two have a common origin. Thankfully, they don't share the same orbit, Otherwise, Phaethon would be one of the Geminids one year, and there wouldn't be much of civilization left after that. But still, they have a common origin. It's interesting that people talk about Phaethon being the parent of the Geminids, because when you look at the published science on this, the assumed total mass of the Geminid stream is actually estimated to be about the same as Phaethon itself. So if you took all of the Geminid meteors and squished them back into an asteroid, it would basically be the same size as Phaethon itself. So they're really kind of more like siblings than parent-child thing. But for some reason, something happened a few thousand years ago, and somehow it split, and one half of it completely crumbled while the other half continues to be an asteroid. But like I say, that's a side note. Nonetheless, because there is this relationship between Phaethon and the Geminid meteor shower, the more reasonable assumption is that dust trail that we're seeing in the Whisper cameras must be some portion of the Geminids. It must be somehow related to the Geminid stream itself. The tricky thing is that the Geminids that Earth encounters are very much on the fringe of what we think the entire meteor shower looks like. So the whole Geminid system is this vast, big cloud of dust in space. Earth happens to only be passing through this teeny tiny little piece of it, like out on the fringes, but we've never seen the rest of the Geminids. We've only ever seen the individual ones that come into Earth's orbit, so we don't know what the full stream looks like. So what we've been doing recently is this is a paper that we've written that should actually get published in the next few weeks. We took some models of the Geminid meteor shower that people had created, and we simulated them in the field of view of our camera. So essentially, every one of these little squares is a simulation of one of these Geminid models in the Whisper field of view. And without getting into the details of this, we've been able to show really confidently that this dust trail that we see in the Whisper cameras is pretty much undoubtedly the true core of the Geminid meteor shower. It's actually the middle of the bulk of the Geminids. Why is this a big deal? Why do we care about this? As I say, fortunately, Earth is way out on the fringes of the Geminid stream. We would never be close to the core. We're never going to get close to it. But as I say, no one's known the full 3D structure of the Geminids, or how massive it is, or where the center of it is, or anything. But thanks to these super sensitive observations from this heliophysics camera, we've been able to kind of unlock one of these big mysteries about this meteor shower that everyone on Earth has been enjoying for so long. And the story doesn't quite end there. So if we go back to the object itself, Phaethon itself, as I mentioned, in 2009, Stereo saw it, and we thought that there was a tail, and like, oh, hey, it's producing dust. Like, great, there's a little bit of activity going on. One of my colleagues a couple of years ago, Ki Cheng, he's out at Lowell Observatory. He was actually my summer student for a while. He had a theory that maybe Phaethon wasn't actually producing dust, that instead it is basically an asteroid, and its surface was fizzing with sodium. It was basically releasing sodium when it was near the sun, not dust. So if you recall a few slides ago, I talked about Comet ISON and the different filters, and how one filter was responsive to sodium and another one was responsive to dust. So what we did in a couple of years ago, we used LASCO. We ran an observing campaign with LASCO. And we took images with LASCO's orange filter, and we also took images with LASCO's blue filter. The orange filter is the one that is very sensitive to sodium emission. The blue filter is really only responsive to dust. And as you can see from the images, it's pretty clear that the orange one, the sodium, you see Phaethon glowing brightly with this, you can kind of see the tail. And in terms of dust, there's absolutely nothing whatsoever. So it seemed to imply very strongly that the tail that we're seeing on Phaethon, and the reason we can see it, is actually because of sodium and not dust at all. And then basically this was kind of conclusively proved because he went on to produce a model of what we think it should look like in sodium, compared those to the observations, and it was essentially a perfect match. Again, there's no way this could be done from the ground. We cannot see Phaethon when it's doing this from the Earth. There's no way for it to happen. It's too close to the sun. We just cannot get this kind of data. And thankfully, we have a heliophysics mission, and because of that, we know so much more about this intriguing object. We still don't know how to categorize Phaethon, but like I say, thanks exclusively to heliophysics spacecraft, we know a lot more than we did. So I know I'm starting to get close to my time now. So what I wanted to do at the end, I threw these in real quick just to cover a couple of recent comets. This comet A3 from last year, many of you may have seen this movie from LASCO before. It's a stunning sequence of images from LASCO where it passed through the field of view. It was an amazing comet. I think George was saying earlier that lots of you have taken images of, or have got images of that comet. What you haven't seen, because no one has ever shown this publicly before, is the movie from our Secor coronagraph of Atlas. So you guys get to be the first people to see Atlas in the Secor images. So you can, it's obviously big and bright. These big bright random flashes that are happening are because of Earth passing close to the camera, and it kind of blinds the camera for a bit. But again, I mean, the images kind of look like LASCO, but it's also really truly spectacular to see, even like the extended tail as it's passing down through the images. And I'll let this run through one more time. And I'll try and pause it at a certain point. Oh, no, it won't let me pause. Okay. So just at kind of the top of the frame, you can almost see like striations and stuff in the comet's tail. So we really haven't taken a deep dive into these data yet, but they're really spectacular images of this comet. And I think that once we finally get around to analyzing these images, we're gonna get a lot of information from them. But what's really unique about this comet's passage, if you noticed right at the end of the sequence, long after the comet had left the field of view, there comes a point in both sequences where you have a very, very narrow, thin streak that appears across the images. This is actually because we passed through the orbital plane of the comet, and essentially what you're seeing here is you are looking perfectly edge on at a sheet of dust. So so very briefly for that short period of time, you're looking so perfectly along it that it appears as this very dense, narrow streak. We've never seen that before from our cameras. And this is why a lot of people saw an anti-tail from the comet. Is essentially you were looking along the orbital plane of the comet and seeing this thing. But it was amazing to see these from space. And then finally, what I want to just bring up right now, because this is happening right now. 2024 G3 Atlas is currently in our LASCO field of view. You can go to soho.nascom.nasa.gov. The images you'll see look like this in the upper right. These are just the regular images. It's very heavily saturated. We're also taking images in filters. So the blue filter is the sequence that I put together earlier on today, where you can see a lot of striations in the tail. And this image in the lower right is one that I saw someone had posted online. They did their own image processing. This is from the orange filter. Again, the structure and the tail structure in this comet is really unique. It's absolutely stunning. So that is something that you guys can certainly follow along on over the next few days. It'll be visible until January 15 in our field of view. So I know I've thrown like a fire hose of information at you guys, but in short, heliophysics satellites, and I really want to emphasize this, heliophysics satellites, nothing to do with comets, no intention for comets, no interest in comets, but nonetheless, from heliophysics, we've learned so much about comet tail striations, solar-wind interactions, chronomagnetic fields, destructive processes, asteroids, meteor showers, dust trails. There's so much that we've learned from these images that were not intended to teach us about comets. And of course, we've discovered more than 2/3 of all officially documented comets. So that's, in my books, that is serendipitous indeed. And with that, I'm very happy to answer any questions. And I'm going to have to, I just heard the bloop that there's a hand raised, but I need to stop, go out of presentation mode so I can actually see that. Okay, yeah, so David.
Not a question, but a comment. In spring of 2018, at our annual big public event, Astronomy Day, I was lucky enough to get Carl to be my keynote speaker. And with a cooler full of dry ice, a bucket of mud, and some other things, and the assistance of Yvette Johnson, our secretary at the time, Carl made a comet for us. And of the 10 big public events that I coordinated, I have to say, without a doubt, that presentation on making a comet in front of the audience there was the most popular we've ever had. So thanks again for that. And good to see you back with Novak again, Carl.
I appreciate that. Yeah, I always enjoy making a good comet. That's always a lot of fun.
Yeah.
So I do see one comment in the, okay, I see John has raised a hand. I was going to respond to a comment that's in the chat real quick. Did all of these comets fall into the sun? No, most of the stuff that I've shown tonight are not comets that got vaporized. But most of the comets that SOHO sees do get vaporized. So of these 5,000 and some that it's discovered, like 4,300-ish of them did get completely vaporized. Yeah, John?
Yes. Well, thank you very much for this. This is really fascinating to see. And this is a little bit of a, I don't know, maybe the question isn't so coherent. I'm curious if this has changed how you, I don't know, the methodology of how you approach observation of these sort of deep space phenomena that don't really have an origin or aren't really evident. Like, is the serendipity, that accident of looking at the sun but finding all of these other things, does it change how you think you might observe other celestial phenomena that might actually be?
So there's a little bit of noise on the line, but I think your question was basically asking if what we've seen so far is changing how we're approaching future observations. Is that kind of the gist of what you were asking? Okay, all right, yeah. Yeah, absolutely. As we see new stuff, we learn more. Like this process I was talking about of using these different like orange and blue filters on LASCO to look at like sodium or look at dust. This is something that we've really only gotten into the habit of doing over the past few years. We hadn't ever fully appreciated the information that that those images were telling us. I wish if I had a time machine, I could go back, then we could extract even more science out of all of these comets, like these ones in the early part of the mission. Like we could get so much science out of these, but it definitely changes things going forward. For all of the missions that I mentioned, one of my roles is kind of the liaison between comet scientists and NASA, the spacecraft mission teams. And so I talk to all of those mission teams if there's going to be a bright comet in the field of view, if we want to do something special with the spacecraft, if we want to ask them to maybe roll the spacecraft in a goofy way, or do something with the spacecraft that they wouldn't ordinarily like to do, then it's kind of up to me to convince them that it's a good idea and they should let us play with their toys for a bit. And they're usually very accommodating. And I think just next month, I think they're doing Parker Solar Probe is going to do a roll for us to observe. I think Phaethon, because we're getting very close to Phaethon. So yeah, everything we've learned in the past absolutely informs us for the future, and we're always kind of thinking back on lessons learned as we approach the next comet. George and Alan. So George first.
What's going to happen with LASCO now that you had the LASCO killer up there? Are they going to keep LASCO going?
Probably not. Right now, the official end of mission is the end of this year. But I think probably what's going to happen is they will keep it running at least until kind of end of September 2026 is the latest I have heard. There are people that are sort of trying to push to keep LASCO going longer, but it's getting increasingly difficult to justify. So I think that probably within the next 2 years for sure, they will unfortunately decommission SOHO altogether.
So you're saying that the cream of the science you can get from LASCO is pretty much finished, and now you're picking up new stuff, but it's not.
Yeah, as far as NASA is concerned, the science from LASCO, scientists will disagree, but NASA, from a programmatic standpoint, argued probably 15 years ago that the science from LASCO was done, and it was really only the pressure from the space weather community, the operations community, that were saying, no, we need this. Like, I know you're not collecting science. And it's a challenge, because NASA's mission is not to do routine operational research. That is somebody else's. NASA's mission is to discover, like, push the boundaries, the frontiers, discover new science. And when the mission stops returning that much science, NASA say, okay, let's do a new one. So this was a big and very complicated, and at times political struggle, for sure.
Okay, thanks.
Yeah. Alan?
Yeah, Carl, thank you. Is the amount of sodium that you see surprising, considering that these are coming from what would be otherwise considered primitive solar system bodies?
Yeah, well, yes and no. I mean, sodium has been seen. It's not unsurprising to see sodium in comets. It's just that sodium isn't normally it's not normally the dominant thing. I mean, obviously with comets, you've got the more common things is your water ices and CN and things are the most common compounds and emissions that we see from comets. But we're not really sensitive to those in our cameras. So in some sense, we've got kind of a selection bias here, that we happen to have a filter that happens to be sensitive to this one thing. So that is what we're focusing on. That said, in terms of things like Phaethon, the asteroid, yes, it is absolutely a surprise to see the amount of sodium that we see coming off of that, and it definitely tells us that that we have quite a bit more to understand about that. And I am working on other research that hopefully will have some publications in the next year or two that show that this sodium emission process is actually very prevalent amongst asteroidal looking things that go very close to the sun.
Is there any chance it's related to the sodium cloud in Eo's orbit? I can't think of a physical mechanism, but I remember in the old days, discovery of sodium was surprising there.
I don't think so. I mean, I just think it's just something that has a certain amount of abundance in the solar system. I mean, one of the cool things about sodium, a lot of people don't realize that Mercury actually has a sodium tail. If you Google it, there have been some pretty spectacular images taken from the ground, some nighttime images where you can see this long tail flowing behind Mercury. That's a sodium tail, and that was actually the appearance of Mercury's sodium tail in our cameras was one of the clues to us that maybe this was something we should investigate. And in one of the papers we did on it, we actually used Mercury's sodium tail as our calibration for the amount of sodium that we were seeing. So it's something that is sort of relatively prevalent in the solar system. It's just not one of those elements that's been given a whole lot of attention because there's other stuff that's easier to see.
Yeah. Thank you.
Yeah. George again?
Yeah, the sodium. Is this the sodium D lines you're seeing? Is it
Yep.
sodium is an emission?
Yep.
Yeah. Okay. Well, then, wouldn't there be, are there any other elements you might see in emission? In the first,
there's a couple of others, and goodness, I'm drawing a blank for some reason right now. There's a couple of others that we might see weekly, but the problem with the wave, the LASCO filters are really quite broadband. Like they're not. It's not a narrowband filter at all.
Yeah.
It just happens that the orange filter is centered pretty much smack bang on the sodium D lines, and the other stuff that you might also expect to see some emission from. It's not nearly as strong in the other filters, but there is something that we're looking at in ongoing research. We have seen some other sort of more exotic stuff. I just, off the top of my head, I forget which ones they are now.
Well, hydrogen, wouldn't hydrogen be one? I mean, the H alpha line.
We don't have H. We don't have H.
Yeah.
Yeah, we don't have H alpha in these filters.
Oh, you don't have it in the filters. No. Okay. You need the ice spectrometer.
Yes.
Okay. Dr. Harry.
No other questions?
When are we going to get a big comet, a really big one like Comet Bennett?
Let me gaze into my crystal ball. So I will say, earlier on, you guys were complaining about observing on cold winter nights. So the G3 Atlas, I saw today a message from a guy, Chris Scher. He's out in Arizona, and he took images of Comet Atlas at noon today from Arizona. It was bright enough. It was 5 degrees from the sun. He had some kind of a baffle that he attached to his telescope, and he got some really nice ground-based images of the comet at noon from Arizona. So if anyone is cold averse, then you could have a crack at it tomorrow. There have been people that have been looking right at dawn as well, because it's just above the sun. So if you do have like a good view of the horizon and you're safe enough, people have been attempting to look with binoculars or whatever just north of the sun. But if anyone is not overly familiar with observing close to the sun, it's definitely not something that we would recommend pointing binoculars near the sun, because that's a fabulous way to go blind very quickly.
Yeah.
So if we don't have any other questions, we're coming up on our time anyway, but we really appreciate your presentation, and thank you for coming back. Maybe next time we can actually have dinner and the weather will cooperate. But we very much, this is certainly an area that I think everyone is interested in, and there's so many parts of it that you brought to the table that people just haven't considered. I'm sure we talk about comets all the time, and we've got a number of people that have posted some recent one. I get things that's of this particular comet on our site, but there's so much out there that's hard to pick. But anyway, but thank you very much for your time, and like I said, we hope you can join us next time at George Mason. And thank you, George, once again for bringing Carl to us, and this has been a very fascinating thing for, I think, a lot of different people. So if we don't have anything else tonight, we're right on time, and so everyone be safe with this weather, and we'll look forward to seeing you next month. We're actually out at the observing sites. I've already had a couple of people say they want to come help outreach and do some new stuff. So we're great to see have those new people. Welcome to the new person also. So again, y'all have a good evening, and we'll talk to you later.